Good day. In this video, we will consider motion that is more general than in the previous video. And we will talk about what happens when a particle is moving in a curved path, but in which both velocity, the velocity magnitude and the direction change. So it's not uniform anymore. Okay. If we look at this figure, what we have is a particle that moved in a curved path, but at each instant, its velocity magnitude and its acceleration is different, right? The direction is different for the velocity, the magnitude is different for the velocity, and also is the acceleration. So at every instant in time, like for instance A, B, or C, we can find the velocity vector, and which is going to be tangential to the path. For instance, when the particle was here, its velocity vector was tangent to this point. When the particle is here, its velocity vector is tangent to this point, right? So when so on, right? It's tangent here. So as we can see, it's an arrow. The velocity is changing all the time, both in magnitude and direction. So we can define points at any point. Here we're just considering 3 points, right? But at any instant, we can find an instantaneous velocity value and acceleration value. In the last video, we saw that radial acceleration is what allows a particle to move in a different direction if you are moving in a curved fashion. The radial acceleration is responsible for changing the direction of motion. But in this case, we also have the magnitude changing. So that means we also have tangential acceleration. So this section in the book deals with a change with motion when you have both tangential and radial acceleration. So at point A, for instance, the particle has a certain value of radial acceleration, which is also the centripetal, which points towards the center of this imaginary circle that we can assign to the motion of this particle at this instant of time. At a different instant, that circle has changed, right? So radial means is also going to be perpendicular to the tangential direction of velocity, right? The velocity is tangential, the acceleration is radial, but it is this one is radial, and then you have this one, which is tangential. So there's two components of the acceleration, and of course we can define a resultant for the two components, right? So at point A, the velocity of the object is only tangential, right? But the acceleration at point A will have two components: acceleration radial parallel to the unit vector r pointing towards the center of the circle, plus an acceleration that is tangential that we can multiply by a unit vector t Chinese hat. That's only one possibility for the notation. This can also be written as AR vector plus a tangential vector. So whatever notation you choose to use, it is equivalent. What is important to understand is that this component is what changes the direction while this one changes the magnitude. Yes, so the total acceleration vector will be at a certain angle. At a point B, well, that everything has changed. You're in a different type of curvature. The velocity is still tangential, right? The total velocity goes like this, tangent to the curve, always, always. So now the circle is on the other side. The curvature has changed. This is a negative curvature. This was positive curvature. Now that the acceleration tangential is decelerating and all that. So what we do is the following. Once you know something is moving, right, you consider your point, your motion, the point in your motion you define your velocity vector that is tangent to instantaneous velocity vector tangent to the motion. And then, of course, we would have two possibilities here. One possibility will be to decompose the acceleration in x and the acceleration in y, right? Decompose the velocity in x and the velocity in y. That will be another possibility, velocity in y, velocity in x. That's always a possibility. However, another possibility is once you have your velocity vector, like for instance here, we decompose the acceleration in x and y because it's pointed like that. Well, in x and y, but here, let's say our velocity acceleration vector is the same. This is the total acceleration just as before. Well, instead of decomposing in x and y, we defined we decompose the total acceleration in the tangential direction, which is parallel to the velocity vector, and into the radial direction, which is perpendicular to the velocity. So what you do is then you define, let's do it at a different point, right? So my velocity was, my particle is here, so I know its tangent, its motion instantaneously is like this. That's the velocity. Well, this defines the tangential axis. And if we had that same acceleration, this one, for a reason, I don't know, any acceleration, whatever the acceleration final is, let's say it's the same one here. Let's say that was the acceleration total. So then I will decompose this one into a radial. You see, radial, which is perpendicular, and let me see, this is ugly, and then a component that is parallel to the v, so that will be the tangential, right? So it's decomposition again, but not with respect to x and y, but with respect to the tangential and the radial unit vectors. Once again, to find the magnitude of the total acceleration, you can do Pythagoras, right, square root, and to find the angle, let's say the angle here, or you do tangent, inverse tangent of AT over AR, depending where you want to find the angle. If it's the other one, then it will be AR over AT. Let's take a look at this example. We have a car driving over a hump. It's a circular section of the road. It tells us that it has a constant acceleration of 0.3 parallel to the road. So at the time the car is at the top of the road, its velocity, it's 6 meters per second. The radius of the hump is 500 meters. So they want us to find the magnitude and direction of the total acceleration when the car is here. So this is helpful because right now, if we're at the top of the circle, we know the velocity is horizontal. And this axis, that's the tangential axis right now, right? So of course the radial axis will be vertical, pointing towards the center of the circle down there. So the constant acceleration the car has parallel to the road at this instant, well, is a tangential and is 0.3 meters per second squared. So that we have half of the problem solved already. What will be the radial acceleration? So for the car to be in circular motion, to keep touching the ground, it is going to need a centripetal acceleration, right? That points towards the center. So that centripetal acceleration we know is v squared over r. So we need this in order, the car needs this, the centripetal or radial, to keep in circular motion. Without this acceleration, the car will just keep moving straight, and that's not what's happening. So we can find the magnitude of the radial acceleration very quickly by just finding the centripetal. So v squared over r, so v squared is 6 meters per second squared, the radius is 500 meters, and that gives us an acceleration of 0.072 meters per second. That's the magnitude. Of course, we see that it has to be pointing towards the center of the circle. That means is going down. The vector will be, or put it like this, will be negative 0.7, sorry, 0, oh my god, my pencil, 0.072 in the negative, or let's put the negative here in the r Chinese hat direction, right? So remember, unit vectors help us label things. So the total vector of acceleration will be positive, will be the tangential plus the radial, right? Or positive 0.300 meters per square second in t minus 0.072 meters per second squared in r. Okay, and if we plot this, it's going to look like this, the tangential and the radial. So the total, we can find very quickly the magnitude of this with some Pythagoras, right? The total acceleration is a tangential square plus a radial square root. So square root of 0.3 plus minus 0.072. Oops, no, it doesn't fit. So there you go. Let me do it again. There you go. And so the magnitude is 0.309 meters per square second. To find the angle phi in that drawing, well, is the arctangent of opposite 0.072 over the adjacent 0.3, and this gives us an angle of 13.5 degrees. So to express the total vector, we're going to say is 0.309 at an angle of minus 13.5 degrees, because as you can see, we are below the x-axis. So one or two more problems in class with this. This is an introduction of tangential and radial acceleration in a curved two-dimensional path.